Hello everybody, good afternoon. This is Mr. Steele. I'm here to complete the differentiation review from 2019. So this is going to be part 2 of that video. Yesterday went off mostly without a hitch. We eventually were able to sign off on the marriage license. Everything's good there, so my friend is married and heading on his honeymoon soon. And got to the Rivercats game and my back wasn't destroyed afterwards. So it's a good sign. Good sign, so let's jump right into this video and get started with the differentiation review. So after yesterday, we focused on just kind of basic problems, kind of a collection of all the basic skills that were there. These ones involve a little bit more of an application. I'm trying to push the questioning just a little bit further each time and trying to make you comfortable with different sorts of setups that involve differentiation, including a numerically presented problem with a table of values, as well as a graphically presented problem with some sort of piecewise function graph that you have to use to analyze. After that, we'll get to the calculator portion. For now, we'll start with question number 16, which involves that table of values I mentioned a second ago. It says the functions f and g are differentiable with derivatives f prime and g prime naturally. Values of the functions and their derivatives at assorted values are in the table. Use the table to answer the questions. So pretty much your standard table, but it is nice to know that the functions f and g are differentiable, which does in fact guarantee us some stuff here that we can work with. So starting off with question number 16, it first starts with a redefinition. It says let's let h of x equal 2x plus 3f of x. We're supposed to compute h prime of 2. So to this, we're going to need to take the derivative of that expression we see up at the top. So we're going to ddx this 2x plus 3f of x. Now if you're thinking derivative properties, technically we're going to be using first the sum and difference property, then the scalar property, but I don't think this particular derivative is too hard to get to. Derivative of 2x is 2, the derivative of 3f of x is 3f prime of x. Given that, our problem would be over, except we're supposed to find h prime of 2. So h prime of 2 specifically will be what we get when we plug in 2. So we'll get 2 plus 3f prime of 2. Once here, we have the value of f prime of 2 up in the table. They tell us specifically f prime of 2 is 4. So in other words, we have 2 plus 12, which is 14. They didn't ask us to do anything else with it, so we're just supposed to find the value of that derivative, which we did. So there it is, pretty straightforward. Just take the derivative like normal. It's almost always in every problem on this test. You're probably going to take the derivative, and then from there plug in any values and read them out of the table. Okay, our second question here, again, involves a redefinition at the beginning. States first that if q of x is equal to x squared over g of x, we're supposed to write the tangent line to q of x at x equals negative 3. Pointing out, of course, that negative 3 is in fact in our table, so we should be able to make this happen. So first of all, that q is usually a pretty big hint, but more than that, we see a function divided by another one. That makes me think of the low d high minus high d low. It's the quotient rule. So I'm thinking we're going to need to use the quotient rule in order to work our way through that. Of course, there are other ways to do it, but I think the quotient rule is probably one of the fastest. But then in addition, we're supposed to find the tangent line. We want the actual equation of the tangent line, so that also means we need to figure out what y is going to be for this tangent line. What is the y value at this point? So I'm going to start with the point of tangency issue. So we're talking about things happening at x equals negative 3. In fact, I'll switch colors for this. And so therefore we want to figure out what is the point negative 3 comma q of negative 3. So based on our function over there, we know that the value at negative 3 is going to be negative 3 squared over g of negative 3. Looking up at our table then, we'll have negative 3 comma 9 over g of negative 3, which is 7. So in this case, we found our point. Those will be our x sub 1 and y sub 1. That's the point where we're going to try to hit that tangent line. So there's our first bet, all taken care of. The second thing we're going to have to hit, of course, is actually computing the derivative. So the slope that we want is going to be equal to q prime of negative 3. What that means is we're going to need to calculate what q prime of x is equal to first and foremost. So in digging in to this expression, I'm going to use the quotient rule as I mentioned before. So low d high, I'll be careful and show it all, minus high d low, once again I'm going to be careful and show it all over low quotient rule. So there is our derivative. It's just not evaluated yet. We got some differentiation to do in there. But fortunately in this case all of those differentiations are pretty easy. For instance, the derivative of x squared, which has to be done in our first term of that numerator, is going to just be 2x. So we'll have 2x g of x. And then we'll have x squared times the derivative of g, which is just g prime of x, all over g of x squared. Now again, be careful. Sometimes I see algebraically people start to cross things out that fall right there. That's not a thing. We can't do that. We have to do the numerator first. It's kind of like the numerator's completely in parentheses. So instead, let's just evaluate this specifically and figure out what we have at negative 3. So first and foremost, if we plug in negative 3, we're going to get negative 6 g of negative 3 minus 9 g prime of negative 3, which again we can find those values, all over g of negative 3 squared. So as far as ingredients, we have g of negative 3. We already had that right here. G of negative 3 is 7. So that's going to be negative 6 times 7 is negative 42. Next we have minus 9 times g prime of 3, negative 3, which is 8. So that's going to mean that we're subtracting 9 times 8, which is 72. So with those ingredients in place, we said g of negative 3 was specifically 7, so that makes this whole thing over 49. And now to simplify this whole thing, 4 and 7 is 11, so I'm thinking this is going to be negative 114 over 49. Now I'm not sure if that's divisible by 7, to see if I might want to simplify it in that numerator. Pretty sure it's not. So what I do know is 91 is divisible by 7. So 98, 105, 112, it's not. So basically we'll stop right there. There is our slope. This will be the slope for our line. And all this means that we can finish this off with our tangent line. It's going to be y minus 9/7 is equal to negative 114 over 49, quantity x minus a negative 3. There is the tangent line that we were looking for. So once again, what I'm hoping you start to realize as you look at these problems is that although we're using a table of values, in reality you're just differentiating and applying those same skills. You're just drawing the information out of the table. So it looks a little bit wonkier, but it's not actually that bad. That brings us to question 18. Question number 18 is called P, which should make you think of the periodic rule. And in fact, when you look here, we see we've got something times something else. So I'm thinking, in fact, we are going to need the product rule. And once again, it's going to be kind of the same strategy as before. Now over here, though, even before we start to think about differentiating, it says evaluate the limit as x approaches 1 of p of x minus p of 1 over x minus 1. So in a sense, they're asking us to differentiate, but they're asking it in the most convoluted, old-fashioned, esoteric way they possibly could. And by they, I mean me, because I wrote the question yesterday. So from here, looking at this expression, what we need to realize is that this fits that form that we saw earlier. It's the limit as x approaches c of f of x minus f of c, the f just being a generic function, all over x of c, or x minus c. And we know that that's equal to f prime of c. And in fact, you know what, just for the sake of naming here, I don't like that. So let's just put a p in there. Let's do that. That'll be better. I like it better. So we know that this should be equal to the derivative of the function at specifically c. So in our particular case, what we're looking for here is p prime of 1. So we're going to need to calculate the derivative of this thing and then plug in 1 to that derivative. So again, that was just using the alternate definition of the derivative, but for us we can start by just calculating p prime of x. So in looking up there, we're going to have the derivative of the first prime second plus first plus second prime. Yeah, see, there's no song. We don't have a song for that one. F prime g plus g prime f. That's the end of the song. No, it's not working for me. There's our stuff. So we need to differentiate this guy. So as far as ingredients here, the derivative of the first function, or the first set up there, is going to be f prime of x times x minus g. Second one will be, let's see, 2 plus f of x times 1 minus g prime. And boy, let me tell you, the number of people who differentiate that wrong and just drop it are so high. So make sure that you actually do differentiate x. That's a linear function with slope 1. So make sure your derivative is 1. It will burn you when the test comes. It's like, ow. Yep, it burns. Be careful. Okay, from here, we found our p prime, so that is the derivative. Now we just need to calculate p prime of 1. So as far as plugging things in, it does take a little bit of time. It's not trivial. And we'll see if any of these things clean up really nice. Again, I just made this up yesterday and I haven't done any written solutions, so I'm working at regular pace. There will probably be a mistake or two in here. Nothing I can do about that. Limited time. So as far as ingredients here, we got f prime of 1, which is 2, times 1 minus g of 1, which is negative 9. So that'll be 1 plus 9. In the second one, we have 2 plus f of 1, which is 10. We'll deal with that in a second. And then 1 minus g prime of 1, which is 1 minus 5. So there is our answer. We just need to simplify this. Clean it up a little bit. That's 2 times 10, or 20. That's going to be 12 times negative 4. Simplifying, that's 2t minus 48, which equals negative 28. So that is the slope of the tangent line to this function p of x at x equals 1. And more relevant was the value of that limit, which uses the alternate definition of the derivative. So there we go. Again, nothing really fancy. This should be just like some of the work that you did on your assignment for the problem set for the product rule. But still, you can see it in action. Works pretty well. Number 19 then brings us to 19. 19 has a C up there. That oftentimes does in fact stand for chain rule. But let's see. F of 3 plus g of x. Yep, I'm thinking this is going to be the chain rule. This looks like a chain rule with all that stuff on the inside. It wants us to find the slope of the tangent line to C. So in this case, it just wants the slope of the tangent line, which means all we're really looking for in this case is we want c prime of 5. We want the derivative of that function c at 5. So we're going to have to figure out what the derivative of c is equal to. Well, the first thing, since it's chain rule, I'm going to play it slow in this case, even though I think you might be able to do this yourself. Oh, excuse me. So first we're going to decompose. We're going to let c of u be something and u be something else. Typically we want u to be what's on the inside. So I'm going to let u be equal to 3 plus g of x, or g of x plus 3. That leaves on the outside f of u. So now when we go to take our derivative, the derivative of c prime is going to be, of course, f prime of u. And the derivative of the inside is going to just be g prime of x. So pulling some ingredients back together, our actual derivative is going to be f prime of u times g prime of x. But recall, we did say that u is equal to 3 plus g of x. That means our derivative is actually going to be f prime of 3 plus g of x times g prime of x. And of course these multiplications, in case that messes with you, it's like you multiply those two together. So some people might even move the g prime out in front. It's kind of your case. I'll do that just for clarity's sake. This is g prime of x times f prime of 3 plus g of x. Okay, with those pieces in place, we now need to figure out what c prime of 5 is equal to. That was specifically what we were asked for. It's going to be g prime of 5 times f prime of 3 plus g of 5. Wow, people are driving really fast and loudly in this neighborhood right now. Go figure. So as far as values here, g prime of 5, going up to my table, is negative 2. G of 5 is negative 6. So we're going to have negative 2 f prime of 3 minus 6. That's equal to negative 2 f prime of negative 3. Oh, look at that. We have that in the table. Negative 2 f prime of negative 3 is negative 1. Which means after all that, our slope is 2. So we get our value out. Once again, recognizing the rule was important there. It was the presence of this 3 plus g of x on the inside, leading us to see it was a composition. So then if we weren't careful or weren't comfortable going fast, we used decomposition to see all the pieces and break it down. We were able to get to our answer of 2. 2 is the slope of the tangent line. There we go. 20. 20 says if the average rate of change of g of x for 5 to 9 is between 3 and 10, find all possible values of g of 9. So interesting, this is just kind of an average rate of change question, but it's using information about what's happening with the function g at 9, and unfortunately, we don't know what's happening out there. So in this case, we're going to have to use the information they provide us about being bounded, or between, these two values to reason it out. So let's start with the basics here. Basic thing that I see first and foremost is it says the average rate of change for g of x from 5 to 9. So I know that's going to be g of 9 minus g of 5 all over 9 minus 5. And then cleaning some of these ingredients up, I see g of 5 in the table. That's negative 6. So that means this expression will be g of 9 minus a negative 6 all over 4. is our average rate of change of g of x for 5 to 9. Now from there, and again just to make sure this is clear, average rate of change of g on 5 to 9. Hey, I wish there was some quick notation for that. Okay, so with that said, what it tells us next is it says that that expression we just have is between 3 and 10. So weird as it is, all we know is that g of 9, actually I'll draw it from red, I thought that's what I collected. G of 9 plus 6, which we said equals the average rate of change of g on 5 to 9, says that value is in between 3 and 10. So that value has to be greater than 3 and has to be less than 10. So now our question is to find every possible value of g of 9. So, and by the way, we're not going to find a finite number, we're going to find an infinite number of real numbers, because we're going to find what's called a conjunction, an inequality on this value. So in looking up here, what I want to do is I basically want to solve for g of 9 in this inequality. So as far as things I can do, I'm going to first multiply the entire inequality by 4. And again, my goal is to get g of 9 by itself, so I'm trying to clear out everything I possibly can. So this gets us 12 less than g of 9 plus 6, which is less than 40. From there, we still got to get g of 9 by itself, so I'm going to subtract 6 from both sides. What this leaves us is 6 is less than g of 9 is less than 34. And we're supposed to find all the values. Those are all the values that we could possibly get. So if you wanted to rephrase your answer, you could say g of 9 is between, and give those two values itself. So g of 9 has to fall between 6 and 34 in order for the average rate of change to be between 3 and 10. So these are really great questions because they're using calculus, but you're answering questions that involve concepts like boundedness and largest and smallest and inequalities. So it's a really rich question. So while the whole test is not written yet, I think this is a good question. I think this is a great way to check your ability to do things with calculus, not just can you perform an operation in calculus. That next brings us to 21. So let L of x equal a piecewise function. It's g when x is larger than or equal to 5, and it's mx squared plus b when x is less than 5. And it says m and b are real, so that's always helpful. Our job is to find the values of m and b such that L of x is differentiable. So the key thing here is to recognize, since we're talking about differentiable, that means that we need to accomplish two things. So now we know that differentiability implies continuity. So if we want a function to be differentiable, it's also got to be continuous. So what that means is that kind of leads us to getting two different things that we need to check. We need to first check L of x. We need to ask ourselves first, is L of x continuous at x equals 5? And I'm saying at x equals 5 because of our boundary. I mean, technically, if you wanted to talk even more, mx squared plus b is a polynomial, so it's everywhere differentiable and continuous. And g of x is given as, where is it, differentiable, so therefore it and its derivatives are both continuous as well. So we're going to answer that question first. Is L of x continuous at 5? Because we've got to have a continuous function to find a derivative. And then second, the new thing that we added in is we're going to check if the derivative is continuous at x equals 5. And in a sense, this last step is what we might call the sharp turn test, or the doink test, pointy point test, the cusp test, however you want to think about it. It'll be our chance to make sure that the derivatives match up nicely and we don't have any of this action going on. We want a nice smooth, whatever's happening, we want a nice smooth curve right there. So that's our goal. So let's start with the continuity one. That's usually a little faster as well. So in this case, what we're going to be looking at is the limit as x approaches 5 from the left of L of x, and we need to make sure that that limit is equal to the limit as x approaches 5 from the right side of L of x. As far as values, we can literally plug in the x values here. We could also do an intermediate step if we wanted. I'm not going to. So on the left, we'll have m times 5 squared plus b is equal to g of 5. And cleaning this up just a little bit, 25m plus b is equal to g of 5, which is negative 6. So there's our first equation. We know that has to be true. In a sense, we were asking, is it true? In a sense, what we ended up with was a criteria. This is the criteria that must be met in order for L of x to be continuous at 5. On the next one, we'll do basically parallel work, but in this case, we're going to need to do the left-hand and right-hand limits of the derivative function L prime of x. So you notice we haven't computed L prime of x yet, so we're going to have to do that off on the side. So I'll do that right up here. L prime of x, without regard to the boundary itself, is going to be g prime of x when x is greater than 5. Again, we're going to hopefully make it so that it's continuous, but for now we're okay. And in the top, since b is a real number, it's just a constant, so its derivative is 0. mx squared will be m times 2x, or 2mx, when x is less than 5. And again, we're not worried about the boundary for the moment. We're using this to check left and right. Again, if we succeed, we'll be able to make this statement true for wherever we place that. So as far as ingredients here, we're looking at plugging in 5. So we'll have 2 times m times 5 on the left. And then on the right, we're going to have g prime of 5. So simplifying a little bit, we'll get 10m. On the right side, g prime of 5 is negative 2. What that tells me is that m is equal to negative 1/5. So right there, we were able to actually find our m value. That's what we need m to be in order to make the derivatives continuous. Otherwise, their slopes won't match up right. So given that m is negative 1/2, it means we have enough information to pull this over into our original function, or into our original equation. So we don't have a true system, we have a very simple system. So plugging it in, we have 25 times negative 1/5 plus b equals negative 6. As far as ingredients, that's negative 5 plus b is equal to negative 6. And adding 5 to both sides, we're going to get that b is equal to negative 1. So our other value here is that b equals negative 1. And so there's our stuff. Unfortunately, I can't demonstrate this one for you on Desmos because it's using a table, but everything looks like it works out. And if you doubt it, you could always go plug in those values. So you could say, well, what happens? Negative 1/5 x squared minus 1. We could check then what happens if we plug in 5 at the original function and with their derivatives. But I'm confident in my work because I'm working pretty slowly. So, voila. Even if there's an error, I think I've worked it carefully and explained it all. Okay, next is 22. So in 22 you're asked, is there a value c with negative 3 less than c less than 1 such that the tangent line to f of x is parallel to y equals 2/3 x plus 42? Explain your reasoning. Okay, let's get real for a second here. This question is the one that's been promised for a long time. Is there a value? Okay, your job when you read that phrase is to think of the value theorems, of which we only know one so far, the intermediate value theorem. So we're wondering about how we might be able to apply the intermediate value theorem to talk about such things as a function f being parallel to some line. So that's what we're trying to answer in our particular case here. Can we guarantee that? Well, let's see a couple different things here. So again, I'm just going to kind of run through all the requirements. So since we only know one value theorem, my thought for the moment is that we need to use the intermediate value theorem. We're going to be dealing with something that involves guaranteeing there's a certain value somewhere. With the IVT, there are two things that we need. You might ask yourself, can I recall them? So what is the first one? Continuity. Yes, continuity is the first requirement. We need to have a continuous function in order to go anywhere. Second thing we need is, of course, betweenness. We need whatever thing we're trying to guarantee has a particular y value to have that value fall in between the endpoints. So kind of a lot to get through here. So second, the other thing we want to think about for the moment is how it is that we can guarantee something is parallel. So if two lines are parallel, and again, this is kind of the thought process. This is all kind of going through my head, I'd say, as I'm working through this. If two lines are parallel, that means that they should have the same slope. That is the literal meaning of parallel in algebra. So we want the two lines to be parallel, which means we want them to have the same slope, which is the same thing as saying they need to have identical derivatives, or their derivatives need to be equal at some point there. So that's got me thinking about information. Basically, I'm thinking about f prime of x, and I'm thinking about y prime of x. So with that said, looking at some of these ingredients here, the first thing I'm going to think about is f prime of x. So I'm imagining, since the derivative of y is just equal to 2/3, what I want is to guarantee that f prime of x is equal to 2/3, somewhere in that interval. So let's start with some of the ingredients here. First, our question is f prime of x continuous? Or I'll state it this way, f prime of x is continuous And can we guarantee that? Well, the answer is yes. It says that f and g are differentiable, so we can state that here. F prime of x is continuous because f is differentiable. And you could say is given as differentiable. That's always nice to communicate, but that's okay. We've cited differentiability as in there, so that's a really good start. Next, we talked about the slopes here and about trying to figure out a way to guarantee that f prime, or the slope of f, is equal to 2/3. Well, on the interval from -3 to 1, looking up here, f prime moves from -1 to 2. So basically what I'm seeing is this. F prime of -3 equals -1, and f prime of 1 equals 2. So most important, -1 is less than 2/3 is less than 2. So we've just guaranteed for ourselves, using the plum-colored pen, continuity. We've just used the red pen to guarantee betweenness. So we've just guaranteed the two qualities for the intermediate value theorem. Now we should be able to guarantee there's a place where f prime of x equals 2/3. So to wrap this whole thing up, we would say, since f prime of x is continuous, and again, we don't need to cite differentiability now because we already wrote it in our work right up here. So since f prime is continuous, and let's see, f prime of -3 is less than 2/3 is less than f prime of 2, f prime of 1, by the intermediate value theorem, and I'm going to write it IVT for the sake of time and space. By the IVT, f prime of c equals 2/3 for some c in -1, or -3, sorry, to 1. And since f prime of c equals 2/3 in that interval, again, it's kind of the special edition of what we had here. Since f prime of c equals 2/3 in that interval, the tangent line to f must be parallel to y equals 2/3 x plus 42, and we'll say it must be parallel at least once. Or let's say, how about this? Let's say at that very c. Boom. So there is our work. We use the intermediate value theorem. This is a tough question. It's asking multiple layers of depth and understanding of parallel and all those different pieces, but I think this is a really good, strong question to ask. I think this really shows a lot of understanding, and I will guarantee you that there will be a question involving that phrase. Is there a value c with blah 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 such that blah blah blah? Explain your reasoning. Like I'm committed this year to making sure that we use those value theorems and talk about them and reason with them as often as we can. So be on the lookout for it. You know it's there. I'm telling you right now, it's guaranteed. Okay, next that brings us to question 23. 23 says let m equal k times g of x, and that's often awfully nice, for some real number k. So basically we're talking about some sort of scalar. Then says the tangent lines to m and f at x equals 2 are perpendicular. Ooh, and we're supposed to find the value of k. So we've talked about perpendicular, I believe, a little bit before, but for the moment, if two lines are perpendicular, that implies that the slopes are going to have negative reciprocal slopes. So that means one slope has to be the opposite sign and reciprocal of the other one. So let's look at a couple different things here. So we're talking about two things happening at x equals 2. So we're specifically interested in what's happening at x equals 2. So let's start there. So first of all, m prime of x is going to be equal to k times g prime of x using the scalar property. So specifically, m prime of 2 is going to be equal to k times g prime of 2. Likewise, we also need to talk about f, and specifically, although we don't need to do a whole lot to differentiate, f prime of 2 is equal to 4. So So now what we've just guaranteed is that k times g prime of 2 and 4 have to be negative reciprocals of one another. And in fact, who am I to say? We have g prime of 2 is negative 4, so actually m prime of negative 2 is negative 4k. Like a really angry advanced television. Negative 4k. So with that, these two numbers, let's do it this way. This and this have to be negative reciprocals of one another. So we need to figure out what that's going to be. So a couple different things here. There's two different ways to solve this. Basically, it depends on which one you want to set as there. So what I want to point out is that this slope needs to be the negative reciprocal of 4. So what I'm going to do is I'm going to say that that implies that our slope that we want is the other one to be equal to negative 1/4. So over here, I'm going to set that equal to negative 1/4 so that the two are negative reciprocals. When we multiply both sides by negative 4, we're going to get that k is equal to 1/16. And there is our value. Now if you preferred to do it a second way, like the other way to do it would be just to reverse that relationship. So we would want 4 to be equal to the negative reciprocal of the other one, which is going to be negative 1 over 4k. So in dealing with this, we'll end up with 16k equals negative 1, and k, ooh, what happened there? How did I mess this up? Oh, it's a negative reciprocal, so it should be negative 4k. Sorry. Should have been negative 4k in the denominator. So that's important. Oh, that's actually okay. So what that means is we get negative 1 equals negative 16k. And from there, if we divide both sides by negative 16, we'll get k equals 1 over 16. So either way we do it, we get the same exact answer. But you can see there's some actual thinking involved here. There's a couple different pathways to get through. This is another one of those questions that asks you to use table values, but to answer some actual like problem-solving kind of questions. And I do think you should be capable of this very thing, because this is one of the many ways the AP exam will push you and force you to demonstrate some real understanding of these techniques. So there is question number 23, the final of our table values. Okay, that next brings us to the second half of this second page. This one focuses on a graphically based problem. So you're provided a piecewise linear function in graphic form, and your job is to answer a series of questions from the problem. Some of these are very straightforward and very quick. Some of these are less so. So let's jump in without much waiting. So for 24, we're going to compute the average rate of change of h of x for x on negative 2 to 5. So simply put, the most important thing to do to start off with is just write out your difference quotient. Oftentimes that is a guaranteed point here, demonstrates that you understand the meaning of that vocabulary phrase, the average rate of change. So we might as well get it in there, make sure it's covered, and in fact I'll even go a little bit further, write this as over 7. Okay, next we need to calculate those values. I think I chose ones that were pretty nice here. So h of 5 looks to me like h of 5 is 1, and we'll assume if there's a dot there, it's meant to be on like the nice intersection lines, or the nice grid lines. H of negative 2, oh look at that, it's 0, that's nice. All over 7 gives us an average rate of change of 1/7. So nothing really fancy there, although I certainly didn't make it easy on you with that picture, but everything looks pretty good there. So pretty fast, 24, good question to start things off. Next is h prime of x. So h prime of x, it wants the derivative of this massive function. The nice thing is we don't need to actually find what h is to write h prime of x. H prime of x is just going to be the slope at any spot on this curve. And the nice thing is, the slope at each of those spots is just the slope of a particular line. So there's going to be 3 different branches. I'll highlight the boundaries themselves first. So we're going to have one slope, which is for x values that are less than 1. We're going to have one slope that is for x values between 1 and 4. We're going to have one slope that is for x values greater than 4. So that's basically all we have at this point. We just need to figure out the 3 slopes of those points. And in fact, we don't need to worry about our equal to, because in looking at this function, we know that that's definitely not going to be differentiable at either 1 or 4. Can you think of a reason why? That's right, it's because there's a sharp turn at each of those points. So basically we can leave it just like this. It'll be very easy to compute. So as far as slopes here, looking at the first one, we go down 1, 2, and over 1, 2, 3. So the first branch of h prime will be negative 2/3 when x is less than 1. In between we go over or up 1, 2, and over 1. So in the middle it'll be 2. Following the same pattern, we go down 1, 2, 3, and over 1, which tells me that our last one is going to be slope -3. So again, it seems like this could be a challenging question when it's asked, but in fact very simple because of the fact that this is piecewise linear, meaning that all we need for the slope function is to figure out the slopes of each part of each linear portion of this function. Okay, third, on 26, that brings us to p of x equaling 3x h of x, and it wants the value of p prime of 3. So before I start worrying about p prime of 3, let's at least get the derivative right. And having graded the AP exam for the last 3 years, something that's become very clear is most of the time you get the first points, the bulk of the points for a particular question or part of a question, just by computing and executing the tool. So in this case, p prime of x would probably be worth a point, maybe even 2. So it might even be worth more points just getting the derivative correct. So let's focus there. As far as techniques that we might use, I see 2 different pieces there. So what I'm naturally thinking of here is that I'm going to be taking 3x times h of x, and I'm going to use the product rule. So in computing p prime of x, we'll have 3x prime times h of x plus 3x times h of x prime. Simplifying a little bit, we get 3h of x plus 3x h prime of x. And now if that's p prime of x, we need to compute p prime of 3. So specifically we'll get 3h of 3 plus 9h prime of 3. And then in looking at our ingredients here, 3 is easy for us to calculate. It's at the point 3, 2. So specifically h of 3 is equal to 2. I can see that right off the bat. And next, h prime of 3 is equal to the slope, which we already saw in the last problem, is also 2. So actually you can make the mistake and switch those 2 by accident and still get the right answer. So that's 3 times 2 plus 9 times 2, which is going to be 6 plus 18, which is 24. So p prime of 3 is 24. That means the slope of that function, 3x h of x, is equal to 24 at x equals 3. Lots of different interpretations. All of them, though, have a value of 24. For 27 redefines m of x as the cube root of x from x less than 2, and f of x when x is greater than or equal to 2, and it wants us to find all x for which m is non-differentiable. So we mentioned this before, there are 3 ways to be non-differentiable. There could be a discontinuity, as in there could be an asymptote or a hole of some kind, a jump. It could be that there happens to be a vertical tangent, meaning a place where the function is continuous but the slope goes to infinity, plus or minus. And then third, there could be a sharp turn, a place where the function is continuous but the slope abruptly changes values so that the derivative function is not continuous itself. So all 3 of those things are things to look out for. In this case, a couple different pieces for us to look at here. Let's see. You can see the okay. So the first thing I see is this cube root. Cube roots are known for having a particular type of discontinuity. They typically are the vertical tangent situation. So basically what I'm thinking right off the bat is that there is a vertical tangent at x equals 0. Now I could be in danger here if x equals 0 wasn't in that branch, like if this were x greater than 2. But notice that we're talking about when x is less than 2, so that's definitely 1. So there is one such non-differentiable point. That was a terrible box, I'll undo it. Okay, the second option. The second option is for us to consider what's actually happening at 2, because that's a place where discontinuities and sharp turns potentially could live. Now first and foremost, what I'll check is whether or not the left-hand limit equals the right-hand limit at x equals 2. So I'm going to ask myself that question. So the left-hand limit is equal to the cube root of 2. This probably isn't going to happen. F of 2 is equal to 0. This is clearly not true. So what that tells me is we don't even need to worry about the slopes at those points. Like that didn't end up mattering at all. What we've found is that there is a jump, aka a discontinuity, at x equals 2. So there was our second non-differentiable point. Our first one was right there. So in this case, what this question kind of baits you into is it tempts you to compute the derivative m prime of x and then check the derivative at 2 before doing anything else. But in truth, it doesn't matter that the slopes don't match up. because the function doesn't even match up either. So basically just something to know. Wasn't going to match up nicely. We got our answer though. Oh, excuse me. Okay, next, 28. 28 says to let c of x equal f of x, and it wants us to write the equation of the tangent line to c at x equals -3. So there's going to be a whole lot of issues that come with this. This is going to be challenging computationally, not necessarily conceptually. So we got a little bit of work to do here. So let's jump in there. I think we can handle this. So first and foremost, normally the point of tangency is almost trivial, but in this case, we need to figure out what c of -3 is equal to get y sub 1, to figure out what the y value is where this thing intersects. So c of -3 is going to be f of -3. And so we've got to look at some ingredients here. So first, f of -3 is right up there. So unfortunately, that's not a very nice position for us to be looking at. So in order for us to get there, we're going to need to first figure out what f of -3 is. Lucky for us, we know some information about that function. Specifically, for x values less than 1, the equation of the function is going to be y minus 0 equals -2/3, that coming from the slope, x minus a -2. So let's just make sure we're at the point -2 comma 0 right there. It's along that same line, so that looks pretty good. So our equation is y equals -2/3 x minus 4/3. And now we specifically want to get what happens at x equals -3. So in our case, f of -3 is equal to -2/3 times -3 minus 4/3, which is going to be 6/3 minus 4/3, or 2/3. So what we just found was just f of -3. So we found the inside of this thing. We now know that c of -3 is going to be equal to f of 2/3. Unfortunately, that means that we need to go figure out what the equation is at 2/3. But at least there's something nice happening here. 2/3 falls on the exact same line that we were just on, so we don't need to get a new line equation. We can calculate that using the same piece that we found before. So -2/3 times 2/3 minus 4/3. That's going to be -4/9 minus 12/9. I just found a common denominator. Is -16/9. So basically there is our y value. So after all that work, we get that the point -3 comma -16/9 is our point of tangency. Whew, that was a lot to get just that little piece. But it's okay. Now we can look at the actual slope. So if we want m, we need to calculate c prime of x first. And specifically we're going to calculate c prime of -3. So keep that in mind. So from here to get there, we first want c prime of x. And we're going to use the chain rule here because of the fact that f of x is on the inside. So in looking here, we are going to get the derivative as the derivative of the outside times the derivative of the inside. But then remember, the inside stays the same initially. So it's f prime of f of x times f prime of x. So now for our specific case, we want c prime of -3, which means we're going to have f prime of f of -3 times f prime of -3. And now before you panic at all the calculation there, this is actually going to turn out pretty nice. So for instance, we already found what f of -3 was equal to, right? F of -3 was equal to 2/3. So a couple things we can do here. First and foremost, we're going to have f prime of 2/3. And then f prime of -3 we have established here. F prime of -3 is just the slope of this line. So clearly that's going to be equal to -2/3 itself. Finally, we need f prime of 2/3, which is like asking what is the slope right down here. But it's the same line, which means that is also equal to -2/3. So in other words, we end up with our slope being 4/9. And with that ingredient in place, that brings all our pieces together finally. We're going to have as our tangent line, we're going to have y minus a -16/9 equals 4/9 x minus a -3. There is our tangent line. I wish I could pull this up, but time, man. Time. Ain't nobody got time for that. So I feel like that's a good start. We're in good shape. And again, our process is good here. Looked much more intimidating than it was, and honestly, the worst work was just plugging into and line after line. So I'd be lying if I didn't say that was annoying, but it's okay. Finally, for this graphical question, it brings us to question 29. It says there's a spider crawling along an x-axis with position h of t. So interestingly enough, this graph is going to describe where a spider is along some sort of axis. So interesting. It says at t equals 5, is the spider moving toward or away from the origin? So basically, as we've done many times before, we need to picture this situation in kind of a weird way. Got this thing here. We've got this little spider with legs. Got our little spider there. And he's crawling along the axis, going all sorts of different directions. Moving around. Oops, I just shrunk the spider. I squished the spider. He's moving around. And we want to figure out at t equals 5 is moving towards or away from the origin. So this is a very classic question type, asking you to interpret both where the spider is and what direction he's going. Because think about it. If the spider is moving to the right, he might be moving away from the origin. But if he's on the left side of the origin, then moving to the right moves him towards it. So it's really relevant for us to figure out both pieces of information here. So definitely a challenging question. So first thing we want to hit, we want to figure out first where is the spider at 5. And since it says that position is h of t, his position at t equals 5 is going to be h of 5. Lucky for us, h of 5 is at x equals 1. So what that tells us is that since he's crawling on the x-axis, he's at position 1, 0 for the moment. So that means that the spider is to the right of the origin. So as of this moment, my picture that I have drawn up above with the spider is totally accurate. We have a correct picture, he's on the right. Now second, we want to figure out the direction the spider's crawling. Because if the spider's crawling left, he's getting closer to the origin. If he's going to the right, he's moving it away from it. So its velocity, which we could call v of 5, is going to be h prime of 5, or the slope of the position function, because velocity is the derivative of the position function. H prime of 5 is the slope right here. Well, looking at this, we've done it already. We have that our slope is negative 3 over 1. So h prime of 5 is equal to negative 3, which means that the spider is moving toward the left. So now thinking about that, if our spider is to the right of the origin, but moving to the left, we can say pretty clearly that the spider is moving toward the origin. And although I would argue that our work up above is probably the work that we need to provide a reason for our answer, we could say because it is to the right of the origin, but moving left. So therefore we get everything in there, and then in this case, as far as the best answer, we'd say toward the origin. So again, really nice question. I think there's one more opportunity to deal with this with the toy train question on the last page, but you can see, great way to interpret, and again, you're using this piecewise linear function to do some high-level thinking stuff. So that is the graphical portion of this review. Well, here we go. We're finally into the last section, or I'm finally into the last section. Hopefully you are too. In the final section, the final page, we're finally giving you some calculator active questions, meaning you're going to need to use the graphing calculator for this. And as I point out in the notes on there, it's very important to remind yourself here that we haven't finished every differentiation rule out there. There are a handful more that we usually stick around and save for when we come back after winter break. So that way we can kind of get back into the swing of differentiation with something kind of new and fresh, but while also reviewing everything that's really important. So when you get into these calculator sections, oftentimes it's in your best interest not to even attempt to differentiate. And even more often, I give you functions that we're not prepared to differentiate. Specifically, if you're looking at these curves here, something I might point out to you is that we have no way to differentiate this part of the function yet, this part of the function, or this part of the function. So in addition to being really crunchy, we also have some things that we just aren't prepared to differentiate. We haven't given you those rules. So you don't want to try them. There should never be a situation where you have to differentiate them. You have to rely on your calculator. for time's sake often, but here because you just don't have the equipment for it yet either. So there we go. So with that said, let's take a look at question 30. Question number 30, the first question from the calculator section, could have come on any section. So this thing looks an awful lot like one of our derivative definitions. And in particular, what I'm looking at here is I'm thinking of the traditional definition of the derivative. The limit as h approaches 0 of f of x plus h minus f of x all over h. So that's kind of where I'm starting, is I'm looking at this guy and thinking about that definition. So, and I know that that definition is equal to f prime of x, the slope function at any x value. But there's one thing here that's different, and I'm not sure if you see it right off the bat. So look back at this expression and tell me if you can see something that's different between that and here, other than the fact that it's using g's instead of f's. I think you might have just seen it. It's right here. There are no x's in our limit of the difference quotient on the left side, even though there are in our original definition. What we have is we've plugged into our derivative definition. So no longer is just in terms of x. What we're calculating in this case is a derivative at 5. So we're going to think about it as someone's already substituted in an x value. So over here, in fact, being more specific, we're literally calculating g prime of 5. So again, I used f here just for the sake of definition, so we don't need that anymore. We want to find g prime of 5. Now, as I said, we're not equipped to handle the derivative of a natural log function yet, much less a true power function, pi, or a numeric base variable power. So that means we're going to have to rely on our calculator to get this job done. So, of course, I don't believe... Oh, I have a giant calculator here. First of all, I can barely see, so I'm going to have to make that really big. Let me clear this stuff out. So as far as g of x, we've got natural log of the square root of x plus pi to the sine of x over 2. And you know what? I'm just realizing this is probably a bad choice to make this y1. So let's just put in the two functions as they are. So even though we only need g for this one, let's just put them both in. 2 cosine of 3 cosine x plus 2 to the sine of x. Okay, so there is f as y1, just easier. We usually think of f as the first function. And the other one is the natural log of the square root of x plus pi to the sine of x over 2. And there is our second. Okay, so I think we've got both. That's y2. We're looking for g prime of 5. That looks good. Okay, so now, if you'll recall, we can graph and find the derivatives where we want to if we graph the function. But I don't want to make a mistake and accidentally choose the wrong function. So I'm going to quit right here. Instead, I'm going to go to Math 8. So in Math 8, we can literally calculate the derivative itself. So we wanted g's derivative at 5. And we called g y2. So alpha trace, or the Widler button. We choose y sub 2. And we can press enter. And it tells us our derivative, which is, it says, negative 0.1625. Oops. So that says g prime of 5, or this value of this limit, is negative 0.163. Or, of course, we could truncate. That's acceptable as well. Either of those answers. The rounded one's what I'm always looking for, but either answer is perfectly correct. So again, in this case, if you'll recall, we went in and we did it using Math 8. We could have, of course, graphed the function. Fun. Could have graphed it. Looking at our thing, we could go to the second Widler button, or the trace button, go to dy dx, and then we were interested in g, which is the red function. We wanted it at 5, so we could get the exact same value we did before. So both options work equally well, so we're in great shape there. Next question, 31. Can you tell I'm running out of gas here and want to be done? I am, and I do. So 31 wants us to write the equation of the tangent line to f of x at x equals negative 2/3. So now this isn't normally a very difficult thing, but because we're using a calculator, it can be a little bit uncomfortable. So if you recall, to get to a tangent line, we need a couple ingredients here. In particular, we need x sub 1 and y sub 1, the point of tangency's coordinates, and we need a slope. So as far as pieces here, to get our m value, we're going to calculate the derivative of our function at that x value, negative 2/3. So we'll punch this into the calculator in just a second. And in fact, that's big enough that I should probably just put this work over on the left side. Pardon me. There we go. So that's our first move. The other thing we need to do is we need to figure out the y value there. That's just going to be f of negative 2/3, or negative 2.3. So we need to calculate that as well. So here we go. Let's pull this up. We're using f, and we want negative 2.3. So again, lots of ways to get here. I'm going to go back out. So first I want to calculate f of negative 2.3. So I'm going to get y1 and put in negative 2. Oops. Negative 2. Why is this fighting me? Negative 2.3. There we go. So remember, this will be the same thing as tracing the actual function, which if we wanted to, we could do it back here. We get the same value, 0.335. And I'm going to put 335.101 in here just to make sure we've got everything. 0.335.101, like the Dalmatians, ... And again, we're probably not going to need to use this again, but you could always store that value as a variable if you so desired by pressing the store button and then doing something like alpha a. And then that way you'd remember that, oh, okay, if we need to use that again, we can just call it a. So now that got us our y value. We want to also find the derivative value. So I'm going to use, again, math 8. We'll do it at x. The x value we want is negative 2.3. And then as far as the function, it's f, which we called y1. So plugging that in, we get that our slope is 3.8679. 3.8679 ... So we got our slope, we got our y value. That's all we actually need to get our tangent line. So in our case, the tangent line that we want, the one we're looking for, is y minus 0.335. It's going to be equal to 3.868 times x minus a negative 2.3. And now keep in mind, because of rounding, I would also fully accept as an answer 3.867 as the slope times x plus 2.3. It's really up to you which way to go. Both are fully acceptable. So there we go. There is our tangent line. Came out pretty clean. This is really just a case of checking if you can plug things into the calculator and use it one step further than just the basics. 32. Okay, good. The last of this section. It says, find the x value for which the tangent lines to G and Y are parallel. So unfortunately, in this particular case, we're going to have a really hard time getting here because we don't know how to compute G prime of x. Like, we just don't have a way. But since this is a calculator question, I'll go ahead and leave it on there and show you that there is a way to let your calculator do the work. Now, and I will say, because my computer works a little bit faster, we should be able to handle this, but it's going to be a little bit tougher here. So, yeah, I'll just go with it. So we want the tangent lines to G and there to be parallel. Remember, we said in an earlier problem that if two lines are parallel, that implies that they must have equal or the same slopes. So in this case, what we're looking for here is we want to figure out when is G prime of x equal to y prime, and then solve for that value. So unfortunately, as we said, we don't have the ability to calculate G prime of x exactly. We'll play with it in just a second. But y prime for sure we can do. The derivative of y is going to be 2/5 x minus 1. So we want to figure out where those two functions actually intersect. So let's see if we can get the calculator to do this for us and see if it'll go reasonably fast. But again, you will not be asked to do this or answer this question on this exam with a function that we don't know how to differentiate. So keep that in mind. I just kind of screwed up the question. Okay, 2/5 x minus 1. Okay, so first and foremost, let's go in here. I'm going to turn off both these functions. I don't know if you knew that, but if you go select the equal signs for a function, you can deselect them by pressing enter. So in here we want to, of course, eventually graph 2/5 x minus 1 and figure out where it intersects G prime of x, which is y sub 2, or the derivative of y sub 2. So to do this, we can actually use math 8 to get it to generate a derivative for us. And this is a little bit weird, but what we're going to do is we're going to tell it to calculate the derivative at any x value. So we'll make it, in a sense, the derivative as a function of x. We'll, of course, use y sub 2. And this sort of nesting makes the calculator move kind of slow. And then in here, I don't know, I'm going to choose it as a variable. So I'm hoping this will work. Well, let's find out. Some people say you could press it with x. Let me try that first, see what happens. Huh. it looks like that actually worked and did something for us. It was certainly different than our previous function. So let's see if that... Actually, hey, we have values, don't we? When we did our work earlier, g prime of 5 was negative 0.163. Let's see if that holds on our calculator. Let's check. Let's trace the derivative function. Negative 0.163. Okay, it looks like we have successfully graphed the derivative of a function we don't know how to differentiate. In fact, there it is up there, n deriv y sub 2, x, x. So, using Zach's notation there. So from here, we want to find the intersection of these two. Boom. Enter, enter, enter. There's only one. It says the intersection occurs at 2.8096. 2.8096, 2.8096, 2.8096, 2.8096, 2.8096, 2.8096. Okay, there we go. So this happens at x equals 2.8096. And so for our answer, we just wanted the x value. So we'll say it occurs at 2.810 or 2.809. And again, this can't be out here, I don't know. Can't be asked on the test because I chose a poor g of x. If I'd given you a complicated function we could differentiate, totally could ask it this way. I just screwed up this question, so just know, oops. But again, still interesting, and hey, you got to see for free how you could actually graph a function's derivative if you so desire. So, what can I say except you're welcome for the sun, the stars, and the sky? Hey, it's okay, you're welcome. Just an ordinary demi-guy. Okay, sorry. So, finally, this brings us to the last section of this assignment, or this review assignment. In this situation, we've got a toy track moving along a horizontal track, and it says its velocity is given by t of t equals that expression. And once again, I'll point out, t of t is a function we don't have the ability to differentiate just yet. So don't get too excited, we're not actually ready to take care of this thing. Instead, though, let's jump right in. So the first question, 33, asks us to find the velocity of the toy train. And now you're probably used to the fact that the derivative of the position is equal to the velocity, because of course it is. In this case, though, we are given the velocity and told that it's t of t. So we don't have to differentiate anything to calculate the velocity here. And to be fair, if I'm being honest, I actually screwed that up and just had to redo this entire part of the video. So here, all we need to calculate is t of 2. And using our calculator, let's see. So you can see I was calculating the calculator stuff there. At 2, we get that our y value is 1.978. So 1.978. And so again, it's not an exact derivative, it's our exact velocity, it's approximate, but there is our velocity. So you can see what makes this question kind of a challenge is you have to read it accurately. You have to read it accurately or else you're just kind of out. You just messed up. Okay, 34, the next question. Was the train moving to the left or the right at t equals 2? Well, if you'll recall, we just discovered what the velocity was. In particular, we saw that the velocity was equal to 1.978. Obviously, that value is greater than 0, meaning that this is a positive velocity. And since velocity includes direction and we're moving along a horizontal track, we consider positive velocity to be moving to the right. So in this particular situation, what we'll say is that the train was moving to the right, or I'm just going to say moving right. And our reason here is because our velocity at 2 is positive. So, and of course I don't want to say v because we're calling velocity t. So I'll say because t of 2 is positive. And of course you could also make a statement like t of 2 is greater than 0 like we did up here. But there is our explanation and our correct answer. Boom. So pretty straightforward because we already had the velocity given. Question 35, determine the acceleration. Well, again, as we talked about, the derivative of position is velocity. And likewise, the derivative of velocity is equal to acceleration. Now, we started with velocity, so we can ignore that relationship for the moment. If we want to find the acceleration at t equals 4, we need to compute the derivative of t. So in this case, t prime of t is going to be equal to our acceleration. What that means is if we want a of 4, we need to calculate the derivative of t at t equals 4. And of course, we can do that using our graphing calculator. In fact, it's already ready to go. We'll use the Widler button, so second trace. We'll go dy dx. Go to x equals, oh no, we're at 4, aren't we? Nice try, I almost screwed it up. T equals 4. When we plug it in, we get negative 2.294. So negative 2.294. And it wanted the acceleration at 4. There it is. We have found it. And what this tells us is the car, or the toy train, is decelerating, meaning it is quote-unquote slowing down, but there's a particular direction associated with this at this moment too. We'll talk about that later on in the course. Finally, the last question we're going to hit, I'm even going to celebrate with a red pen to finish this thing off. It says there's a second train moving along the same track with position S of t for t greater than 0. That seems like a terrible idea, and these trains are probably going to run into each other at some point. It then says if the first train is at position 7 at t equals 6, are the two trains moving toward or away from each other at time t equals 6? So basically we've got two situations to deal with, and we need to take into account position and velocity so that we get that direction built in as well. To help me organize this, I'm going to draw the train tracks itself. So I mean, if you wanted to, you could literally go like, that way it's like choo 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 choo. So there are our train tracks. Let's see if I can copy and get the train tracks to look right. Ha. There are our train tracks. So what we know so far with our first train, we are told that it's at position 7 at t equals 6. That's a really important starting thing to know. That tells us where the thing is literally. So I don't know, if we say that 0 is right here, the first train is going to be somewhere to the right over here. Actually, let's make it a little closer. First one is right here, and this is at 7. So it's sitting right there. Next, we want to figure out what direction that car's traveling, because we're trying to figure out are the two trains going toward each other and with imminent danger, or are they going apart from each other and going in opposite directions? So to do that, of course, we knew that the original position was 7, but we need to figure out what is this derivative at t equals 6. So doing a quick little approximation, or using the calculator to find that for us. Second count, we'll go option 6. We're interested in 6. It says that derivative is 2.50. Oh wait, the velocity. I did it again, didn't I? We are given the velocity of the train, so we don't need to find any derivative. We just need to see what the value is at 6. And it says at 6 our value is negative 2.784. 2.784. So what I see is the velocity is negative, which means the train is driving to the left at that moment. Doesn't mean it won't run into the thing some other time, but we know for sure it's running to the left at that moment. Now second, let's look at the second train. So we're interested in what that second one's doing. So the first thing I need to figure out is what is S of 6. So in here with my calculator, let's make it a little smaller. I'm going to brave it for the moment. This one we have, it looks like x or t to the 1.6 plus 3t. And again, we're using x in the place of t, that's okay. Plus 1. So let's make sure this is big enough for me to read. Yep. Okay, if we graph this, we want to know what's happening at 6 for that one. So let's make sure we're on the correct one. By the way, you can move between graphs by just moving the up and down arrows. We'll see what happens at 6. It says it's at 34.581. 34.581. So that means the second train is somewhere way the heck over here. 34.581. So we know that. The question is, are they moving towards each other that way, or is this one moving to the right? I hope it is. To answer that question, we need the velocity of the second train. So easy enough. We'll just calculate its derivative at 6 on the calculator. So in here, we'll go second trace, 6, and we'll see what's happening at 6. Oh, I'm on the wrong graph. Notice it's easy to do that. Second calc, 6. I need to make sure I'm on the red graph. There it is. We're going to see what happens at 6. It tells me dy dx is 7.688. And so that's telling me, since that value is positive, I noticed that I dropped a 0 over there, but since this value is positive, that tells me that the second train is moving to the right, and that combines very quickly to say that these two trains are moving away from each other. And with that said, finally, having had to do this last problem multiple times because of my own mistakes, we have completed this review. I hope it has been helpful, and I hope this helps you achieve very well, with or without my absence. So thanks for watching. Keep getting better and learning to differentiate all the techniques. Do a great job on Thursday on that test. Have a good night.